Hi, I'm in San Diego and I'm making a video for 11.2. And I think Jeffrey, right, is in well, he's in California. Who else is in California? I'm not sure. So yeah, we could add office hours here. But anyway, I'll be here all week for a conference, so I'll try to keep up the best I can with homework problems and stuff. I'll be able to at least I'll be able to text, no, not text, but email you back from my phone if you write during the day, and then at night I can probably have more time to answer things. Let me see. So to me, this is the big reason why we have moment generating functions. I mean, why we use them. It's a nice way of finding sums of random variables. And we do this through moment generating functions. So everything happens very nicely. So this is the property I'm going to use. If x and y are independent random variables, then the moment generating function of their sum is the product of their moment generating functions. And so you might think, oh, what does this do for you? But when you find this product, then sometimes it's the moment generating function of an already defined random variable, because remember we have that list of all the common moment generating functions. Maybe you can go backwards and then find out by using the moment generating function what random variable that represents. So it's that nice two-way. I mean, the recognition doesn't mean a lot in that last section, but now when we put two together, it's nice to go backwards and say, oh, that must be the moment generating function of an exponential or a normal or whatever. I think through a few problems I can show you what I mean, and here is the proof of that. So the theorem: if you have n random variables that are independent, we have to have independence, then the moment generating, with these are the moment generating functions of each of those random variables. Then the moment generating function of the sum is equal to the product of the moment generating function. So the proof of this, we need an important fact back from section 8.2, the expected value of g of x times h of x, where these are functions of random variables. So maybe this is something like expected value of x squared times y cubed. If x and y are independent, this would be the expected value of x squared times the expected value of y cubed. And that's what independence can do for us. So I'm going to use this fact in this proof. So this is a nice proof. I mean, when I did it in class, and even when I do it in general during the quarter, people are like, well, what did you do? It's really just using definition to manipulate it and get back to what we want. So the moment generating function, here's the sum of a bunch of random variables of t. So by definition, this is the expected value of e to the x1 plus x2 plus xn times t, which is the expected value of e to the x1t times e to the x2t times e to the x3t plus, times e to the xnt. Now I'm going to use that property. Since x1, x2, x3 up to xn are independent, I can rewrite this as a product of expected value of e to the x1t times e to the x2t times e to the xnt. But this is just the definition of expected value of x1. So this is, this is the definition of the moment generating function of x1. So this is mx1 of t times mx2 of t all the way times mxn of t. So the moment generating function of the sum is the product of the moment generating functions. And then hopefully when we put this together, then we see, because every random variable has a unique moment generating function, maybe we see this as a unique one, and we can go backwards and say what random variable that is. So, for example 1, let's see, yes, I want to show that two normals. We use this all the time in statistics. If x is a normal random variable and y is a normal random variable, here's its mean, standard deviation. Here's its mean, standard deviation. That if I sum those two random variables, I still get a normal random variable. And I think we kind of take this for granted, you know, in statistics we do it so often. If you sum two normals, you get a normal. And I'm not talking about a mixture. I'm talking about you sum a bell and a bell, you get a new total bell. I'm not mixing them. I'm actually adding two normals to get a normal. So let's show how to do this. So let's look at the moment generating function, and these I should say, oh, very nicely, they're independent. So this is oh, how do I erase this? All right, I have a nice eraser somewhere here. I think I just lasso, right? And then just delete it. Okay, so let's go back. The moment generating function of the sum. So m of x1 plus x2 of t. I'm going to see if this is unique or something I know. So I know this is just the product of the moment generating functions. Sorry, I actually used x and y, because this is x and y. So x and y. Well, what's the moment generating function of a normal with a mean of this, a standard deviation of this? So I have my chart here. Let's go down to a normal. I don't see it on that page. Okay, there's a normal, and there's its moment generating function. Okay, so let's go back a minute. So this is e to the mu xt times, let's look at that again, half t squared sigma squared. So half sigma x squared times t squared. Okay, and let's see, moment generating function for y is e to the mu y t plus 1/2 sigma y squared t squared. So we can combine those. I'm multiplying 2e, so this is e to the mu xt plus mu yt plus 1/2 sigma x squared t squared plus 1/2 sigma y squared t squared. So writing it a little bit more nicely, this is e to the mu x plus mu y t plus 1/2 t squared sigma x squared plus sigma y squared. So we recognize this as the moment generating function for normal, where, let's highlight it here, this is my mean and this is my variance. So what we've just shown then is that when I add two normals, I get a normal, because I get a moment generating function of a normal, with the new mean as the sum of the means and the new standard deviation as the square root of the sum of the variances. So, I mean, here's my new, right? This is my new variance, so standard deviation would be the square root of that guy. So this is very helpful in doing problems. Now I know the sum of two normals is normal. I know what the mean would be. I know what the standard deviation would be. So let's switch to blue. Okay, the weight of a math book is normally distributed with a mean of 5 pounds and a standard deviation of 1 pound. So let's xi. There's a probability that 3 independent copies of these books in your book bag weighs more than 12 pounds. So let xi be the weight of the ith book, and each book is normally distributed with a mean of, let's see, 5 pounds and a standard deviation of 1 pound. So what example 2 is saying to us is if we had 3 of these books in our backpack, then their weight should be normally distributed with a mean of mu1 plus mu2 plus mu3 is 15, and then the standard deviation is the square root of 1 squared plus 1 squared plus 1 squared. So the weight, let's just call this the total weight, W, is normal with mu of 15 and sigma as the square root of 3. And so what was the question? What's the probability these books weigh more than 12 pounds? So what's the probability the total weight is more than 12 pounds? I'm just going to do it like we do at a z-score. That's the probability that a normal 0, 1 is greater than 12 minus 15 divided by square root of 3. So this is the probability that z is bigger than, I'm sorry, I didn't figure this out beforehand, whatever a negative 3 divided by square root of 3 is. And then I would look up in my z table whatever value this is and estimate the probability. So this goes back to normals and z tables and reading them. I think I'll just stop and then start with a new video in a second, just because this is probably getting long.